I'm Simon Clark. I'm the Director of the AMSI Summer School at Monash University. Before I start, I wish to acknowledge the people of the Kulin Nations on whose land we are gathered today. I pay my respects to their elders, past and present. It's a pleasure to introduce tonight Professor Nick Trefethen, FRS. Nick is Professor and Head of the Numerical Analysis Group at Oxford University, a Fellow of Balliol College and the US National Academy of Engineering, and Global Distinguished Professor at New York University. He has won numerous international prizes, which I won't go into here. However, his most important claim to fame, he was the first commercial customer for MATLAB. Nick is Professor of Numerical Analysis. Why is numerical analysis so important? I won't go into that, as Nick has answered that in his essay, What is Numerical Analysis?, which you can find as the appendix of this book here. However, it allows the development of faster and more accurate algorithms to study fundamental computational problems in fluid dynamics, finance, biology, optimisation and many other fields. Nick is known as a passionate and lucid communicator of mathematics, and the awards he has received reflect this. He has written 5 books on a range of topics in computational mathematics and numerical analysis. His books are known for being well written and making mathematics as easy to understand as possible. His book on numerical linear algebra, this book here, is the all-time bestseller for SciAm books. Tonight he will speak on the eternal divide of mathematics and science, discrete or continuous. Thank you very much, Nick.
Thank you very much, Simon. Can people hear me? I guess so, okay. It's thrilling to be here. I have a long-standing relationship with Australia. I came here by ship at age 9. We left Los Angeles and 28 days later came to Brisbane. And I went to school for a year in Australia, which was terrifying. You know. I'm from America. I'm from Massachusetts. And to arrive in the old days in Australia with, the girls wore gloves, of course, and the boys got whipped with, rulers if they misbehaved. And it was an amazing experience, and of course I loved it, and I've kept coming back ever since. In fact, this is the first time in my life that I've ever been to Australia without going around the world. So it's my 6th visit, but the other 5 were part of long journeys around the world, staying for a long time in Australia. So this place means something to me. Mathematics also means something to me, so I'm a mathematician. It's not going to be a mathematics lecture particularly, but what it is a lecture from the point of view of a mathematician. So I want to talk about a lot of different things with this theme of discrete and continuous, and probably only a math guy would put it together the way I'm going to put it together. I'm hoping that everyone in the room likes science. I know many of you like mathematics because there are 100 of you from the summer school. But I hope all of you like science also. And as you'll see, the talk will have many parts, and you'll know some of them better than others, but that's okay. So let's get started. So there's the background, if you like. The theme is discrete and continuous. And so there we have a random scene from a random city. And just to remind us that the physical world looks pretty physical, and more specifically, it looks pretty continuous. Stuff like that just looks like continuous matter. The talk isn't all about matter, but that's the most obvious case of something that has both a continuous and a discrete side. But actually, it's a 14-part talk, so there are the 14 parts. What I'm going to do is actually take a minute or two on each of these subjects. I've picked 7 areas of the sciences, and in each I'm picking 2 subjects in that area where there's something interesting to be said about how continuous things relate to discrete things. So hopefully when you look up at that list, you see a few areas that you're pretty comfortable with and maybe some areas you're not so comfortable with. So among other things, maybe this will be an interesting way to be reminded or exposed to some interesting scientific ideas. But the theme is always discrete and continuous. So the outline couldn't be simpler. I will now begin in the upper left. Well, we all know what atoms are, of course. So physics is the study of what makes our world what it is. And I want to begin with the famous Feynman, who wrote the most important physics textbook ever written, the Feynman Lectures. This was the great genius. I'm sure many of you have heard of him. Who's read Surely You're Joking, Mr. Feynman? Hey, I'm impressed. That's fantastic. By the way, the Feynman Lectures on Physics, this great book, you can get them in audio. He was recorded in 1963, and I've listened to some, and they're fantastic. He's so ethnic. He's from Brooklyn, New York, and his voice doesn't sound like Einstein. He sounds like a baseball fan from Brooklyn, New York. But anyway, he begins, page 1 more or less, of this great work. I'll read it to you. He says, if in some cataclysm all of scientific knowledge were to be destroyed and only one sentence passed on to the next generations of creatures, what statement would contain the most information in the fewest words? And then here's his answer. I believe it is the atomic hypothesis, or fact, or whatever, that all things are made of atoms, little particles that move around in perpetual motion, attracting each other when they're a little distance apart, but repelling upon being squeezed into one another. In that one sentence, you will see there's an enormous amount of information about the world if just a little imagination and thinking are applied. So that's pretty good. That really is how he begins his great work, which has influenced generations of students. You may know that in the olden days, the Greeks had some ideas about the world being made of particles, but they didn't really know anything scientific about that. That came later. I love numbers. So I can't resist giving you some numbers as we go. The Earth has about 10 to the 50th atoms in it, so that feels pretty continuous. 10 to the 50th is huge, but it's finite. It's a finite number. If I take a handful of matter like this, it has about 10 to the 24th atoms in it. Now that's the square root of 10 to the 50th, roughly. Is that a coincidence? I don't know, probably, but I'm not sure. Square roots come up in funny ways. Humanity famously lives in this intermediate zone between the very small and the very large. The gas laws are things about pressures and volumes of gases and so on, and those laws were developed in Oxford, where I work, at a time when people thought of the world as continuous. So Boyle and Hooke, those were the guys in Oxford. They didn't know about atoms. They weren't thinking in terms of atoms. That came later, 2 centuries later, when Maxwell and Boltzmann figured out that the way gases work depends on their discreteness. So I want to tell you an example, or 2 examples of that. So let's suppose you take a volume of gas, a balloon or something, and you shrink it to half its size and make sure the temperature stays the same. Well, the pressure doubles. So that was known in the 17th century. Why does the pressure double? Well, it's because it's got the same amount of atoms in there traveling at the same speed that they used to travel, but now they're hitting the wall twice as often. So that's why the pressure doubles. That was figured out in the 19th century. A better one, more fun, take your balloon, double the temperature. Don't change the size, double the temperature. That also doubles the pressure. Why? Well, Hooke and Boyle didn't know why, but in the 19th century they figured out why. When you double the temperature, each atom, molecule, each particle goes the square root of 2 times faster than it used to. Square root of 2. So what does that mean? Well, it means that they hit the wall the square root of 2 times more often, but also every time they hit the wall, they impart the square root of 2 times more momentum. So isn't that an amazing implementation of a simple law? Doubling the temperature doubles the pressure. Why? Because the square root of 2 times the square root of 2 equals 2. It's amazing. So that's an example of how something very continuous, this old law of physics about balloons, has an implementation that is discrete, involving these atoms. Okay, I think I'll move on to the second physics one. So quantum mechanics is a subject everybody's heard of course, and most of us don't really know very much about, and I'm sure that's true of many of you. But it's a famous example, again, in physics, where the discrete and the continuous interplay. Let me give you a flavor of where some of it came from. In the 19th century, they started doing experiments which led to observations that were strangely discrete. So here, for example, 200 years ago, Fraunhofer looked at the spectral lines coming from the sun and noticed these black things in the spectrum. You know, what's going on there? These particular frequencies that weren't present in the solar spectrum. Years later, it's figured out that that's all about certain wavelengths of light being absorbed by certain atoms in the sun. And the reason is quantum mechanics, the great theory of discreteness in fundamental physics. So this is a quick history, of course. You've heard of Bunsen burners. They did related things a few decades later. Einstein, one of his great works of 1905, essentially invented the photon, which is the idea that light is discrete. Light feels continuous, but Einstein really pinned down the fact that it's made of photons. Not long afterwards, they realized that even matter has a discrete and a continuous interplay. And there's just a picture of the kind of mathematics that turned out to underlie this stuff. Now, I'm sure some of you know what eigenvalues are, and some of you don't. I happen to be very interested in eigenvalues. They're a mathematical idea, which is all about discreteness. You take a continuous mathematical object, you analyze it, you get certain special numbers called eigenvalues. And I don't know if we're allowed to have a little risque material in this talk, but I'll tell you about Schrödinger. So, maybe we need to turn off the cameras, I don't know. Schrödinger was a dude, so he was a great genius, Austrian physicist, and every Christmas holiday he would take a mistress up to the Alps and go skiing. And he had done this for a number of years, and then in 1925, it's December 1925, he did the usual thing, but it seems he was unable to concentrate on her because he'd had this amazing idea that eigenvalues were discrete things, and observations like those probably must be related to eigenvalues. And he was a great genius, and in a matter of a couple of weeks over Christmas holiday in the Alps, he figured out the essence of the matter. And then the next year, 1926, was when Schrödinger's equation appeared, and from that follows such an amount of science, of physics and chemistry. So the mistress didn't get much attention. I believe that I've looked at the lists. About 30 physics Nobel Prizes are related to eigenvalue problems, which are all about discreteness. Pictures like that, energy levels of atoms, discrete observations in physics are everywhere. It's just astonishing. So that's a 20th century discovery. Let's move on to chemistry. So we've all heard of the periodic table. Many lecture theaters have one, but we don't have one here, I guess. So you all know that picture. That's a great example of how you might expect the world to be continuous, and it isn't. So, suppose you're just a caveman or a cavewoman, and you look around your world and you see stuff, right? It would never occur to you that that stuff was made up of roughly 90 different types of stuff. But it is. And slowly that understanding emerged. It was known certainly before the periodic table came to organize it, but starting in the, 1860s, Mendeleev, it was realized that the stuff the world is made of has this alphabet. It's just a rather big finite number of different ingredients. with this tremendous structural order in them. An amazing discovery. This is in the news again, by the way. So as you may know, not long ago, well, first we had the black holes merging a couple of years ago, but in August there was the observed merger of a neutron star, gravitational waves from a neutron star merger. And it turns out that has led to a whole new understanding of where some of these elements come from. If you look up at number 79, gold is up there at 79, and it turns out that our understanding of how the elements gold and beyond are manufactured in the universe has been affected by this neutron star merger. It's just astonishing the way things interconnect. But anyway, chemistry is built on this discrete alphabet. By the way, I don't know much about chemistry, so probably I know more mathematics than most of you, but I'm not at all sure I know more chemistry than half of you. It's a subject I skipped a year in high school, and that was the chemistry year. So I've never taken a course in chemistry, but you should all take courses. Kind of a more incredible discovery because we sort of take it for granted, and you hardly know about this until you remind yourself. First of all, what does stoichiometry mean? That's a complicated, weird word. It's easily forgotten. But it means this flabbergasting fact that was discovered when the chemists began doing their thing a couple of centuries ago. When chemical reactions occur, they always involve integers or rational numbers. So there's a picture, maybe you can recognize the molecules, so that's methane plus 2 oxygen molecules burns, and out comes carbon dioxide and 2 water molecules. Now, of course, the people discovering this didn't have that picture. What they had were experiments that showed, weirdly, that the amount of methane and the amount of oxygen had to be in just the right ratio in order to get a clean reaction, and out would come precisely always the same ratio of carbon dioxide and water. You think about that, it's not obvious at all, right? The caveman would figure, well, stuff might do stuff, but why should the amount of stuff always have this rational relationship? So that was a big, big discovery, and a key person there is Dalton, who was one of the discoverers of the atom, in effect, because he reasoned back from these observations of chemical reactions. He reasoned back and figured the world had to be discrete. That's how chemistry is implemented, discretely. So, sort of related, though sort of different. You've heard of Avogadro's number, 10 to the 23, more or less. It's a big number. If you're like me, you've heard of it, and you can easily forget what it means. So let me remind you. Another astonishing discovery. If you have a balloon of a certain size at a certain temperature, it has a certain number of molecules of gas in it, and that number is the same whatever the gas is. It could be oxygen, it could be nitrogen, it could be helium. It's always the same number. How weird is that? So that was a great discovery of a few centuries ago, and it's again an aspect of the discreteness that underlies our chemical world. Okay, I think we've finished with physics and chemistry. Let's get on to biology. So cells, obviously, that's a case of discreteness. These had to be discovered. This is another case of Hooke. So, obviously, in the olden days, I said Aristotle, it was not known that living things were made of cells, but then Robert Hooke was the great name who essentially discovered this because he was studying things with a microscope. He started looking at things in the 1660s, and he found things like this. That's not his drawing, but he made wonderful drawings of how just about everything is made of cells. How surprising is that? So, imagine you can think about God designing animals, or you can think of natural selection designing animals. It doesn't matter. Either way, it's not at all obvious that they're going to be made from cells, is it? And yet they are. With hindsight, we can imagine it would be pretty hard to design me just out of stuff. How would you organize stuff, right? You need some kind of discrete structure like that. That seems kind of obvious to us now, but it was a great discovery of biology. The other, sorry, I like my numbers. So the human body contains about 10 to the 13th human cells and then about 10 to the 14th bacteria. But they're much smaller, of course. You're mostly non-bacteria. So the other thing in biology to mention, of course, is DNA, and we all know about that one, the famous alphabet in the sciences. So maybe you don't know the phrase, the central dogma. This is a phrase coined by Crick, as in Watson and Crick. So the central dogma of DNA is that DNA is transcribed into RNA, which is then translated into proteins. That's how we're all made. The DNA goes through this process and out come proteins, which then roll up into three-dimensional objects. There's something amazing. Our whole code is one-dimensional, and yet we're three-dimensional. Isn't that strange? It's a one-dimensional discrete code that has to somehow generate a three-dimensional body in this world of ours. You'd never cook that up. It's too unobvious. But with hindsight, how else could you possibly organize something? You couldn't write a three-dimensional code, You don't write books three-dimensionally. They start in the first word and go to the second word. So, another great example of discreteness, which Darwin famously did not know about, even though Mendel was doing experiments at the same time, which might in principle have informed Darwin. He didn't know. So we've got about 3 billion base pairs in our genome. And okay, I guess those are my three starting sciences. So we've talked about physics, chemistry, biology. So we're 6/14 of the way through. Now let's get to mathematics, which of course is my home territory. This is the one we're going to go back the furthest in history. And as always, I want to mention two parts of mathematics that have this discrete continuous interplay. And the first has, we start with geometry. The Greeks were the great geometers. They figured out how to do geometry in a rigorous fashion with axioms and proofs and all that. That's pretty continuous, isn't it? You draw a triangle, everything is totally continuous, nothing discrete about that. But I want to mention two crises of mathematics. Maybe they're the two biggest crises of mathematics. I don't know. Both related to the whole discrete continuous interplay. So the first one was the ancient one, the Greeks. You probably do know that somewhere along the line, the Greeks discovered that the square root of 2 was irrational. They didn't say it that way, of course. They thought in terms of geometry and the length of a hypotenuse, but somewhere along the way, they realized they could prove rigorously that that length of that hypotenuse was not the ratio of one integer by another integer. It was not a rational number. So their concept of number was discrete, rational, m over n. But their concept of geometry was, of course, continuous, because geometry is sort of obviously continuous. So this great crisis was the inability to match up the discrete numbers that they understood with the continuous geometry that they understood. I don't think anyone really knows the history too well of what happened with the Greeks. What did Pythagoras do and so on? Did anyone commit suicide because of this fact? There are urban legends about that. But anyway, they were upset. Then I want to fast forward a few millennia. Maybe I'll tell you one more thing, though. No, let's move on. So another great crisis was in the 19th century with Cantor, George Cantor. So he was the mathematician who made the notion of infinity rigorous. And along the way, came up with these astonishingly unexpected facts about infinities, that they are of different sizes. And I'm sure many of you know this. The idea of finite versus infinite is kind of obvious and easy. There's no big deal there. If you take the numbers 1, 2, 3, 4 and keep going forever, that's an infinite set, obviously. But what Cantor proved was that not all infinities are equal. And in particular, the famous case would be if you look at the integers, or indeed the rational numbers, That's a smaller infinity than the set of all the numbers on the real line. So if you take all the points on that line, that's a bigger infinity. I don't know if you've heard the story of Cantor, but it's an awful story. He made these discoveries. Many people attacked him. Some immediately realized how true and important this was, but others, well, some thought it was false and unimportant. Others thought it was true and awful. Everything went wrong. It's violated people's feelings of how things should be. And Cantor spent time in mental institutions, he was really deeply traumatized by the reaction his theorems got. But now, there's no dispute about any of this. It's accepted as fact. The integers are the same size as the rational numbers, but the continuum of all real numbers is bigger. And what makes it even weirder is you might ask, is there anything in between? And it's known that there's no answer to that question. It's neither yes nor no. You can never prove that it's yes. You can never prove that it's no. So all this weirdness leading to this other crisis in mathematics. That was just my first mathematical topic. The other one is the difference between algebra and analysis. So, well, we all know sort of what algebra means, and analysis is like calculus on steroids. You know, it's the continuous part of mathematics. This is a huge, huge distinction. And most mathematicians at heart think of themselves as much closer to one of these or to the other one. I'm on the analysis side. I'm sure you people are a mix. So you could say this is one of the two great divides among mathematicians. The other one is the more famous one of pure versus applied, and I'm on the applied side. But, you know, algebra is interesting and pure mathematics is interesting, but we all affiliate with our team, don't we? I found something on the web. I was looking to see how people felt about algebra versus analysis. So there's something there. Well, you've obviously read it. Should an analyst feel inferior? And then this poor person, I have a general question on choosing a subfield. I personally find analysis interesting, engrossing, and fun, and I find I'm better at it. On the other hand, I can't help but feeling that other subjects are more abstract and advanced, and this makes me feel inferior. Isn't that amazing? Okay, so among those of you who do feel that you're somewhat mathematicians, raise your hand if you feel closer to the algebra side. Okay, and to the analysis side. Oh, that's very even. That's great. And I guess while we're doing it, how about the pure side? And how about the applied side? Wow, so this is a scientifically constructed audience where whatever I ask, it's going to be 50-50. Very impressive. One of the aspects of this is that, in my experience, younger people beginning to get interested in mathematics often are attracted to the discrete stuff because often the problems can be posed more simply. And the great example is in number theory. You know, you can ask, are there infinitely many prime pairs, you know, like 5 and 7? Anybody can understand that question, whereas questions of analysis tend to be harder. On the other hand, as you get more and more advanced, sometimes the discrete stuff turns out to be harder than the continuous stuff. And number theory is one of the hard branches of mathematics. Okay, so now we get to the epicenter of the human civilization, my field. So numerical analysis is the study of algorithms for solving the problems actually of continuous mathematics. So it's got a bias in there. It's well, as Simon said somewhat, it's the field that enables a lot of modern science and engineering. When you compute something on the computer, and you always have to do that, you're probably using algorithms developed by people like me to solve differential equations or solve matrix problems or find eigenvalues or optimize functions, all sorts of things like that. That's what this field is. But I want to mention, as always, two discrete continuous parts of the subject. So first of all, machine arithmetic. By that I mean, how do computers represent numbers? We've just mentioned that the set of real numbers, on a line, is a continuum. It's infinite. It's not even a small infinity. It's a big infinity. So, of course, your computer can't really represent all of those infinitely many numbers. It can only deal with a finite subset. When I was very young, they hadn't settled on how to do that, so different computers did it in different ways. But then in the mid-'80s, the standard method was adopted called IEEE arithmetic, and now most computers represent numbers the same way. And in that standard method of representing numbers, you have a discrete set, and between 1 and 2 on your computer, there are, I think it's 2 to the 53 numbers, which is about 10 to the 16th. Then between 2 and 4 on your computer, it's the same. There's another 10 to the 16th. And between 4 and 8, there's another 10 to the 16th. And between 8 and 16, another 10 to the 16th. So that's how computers discretize the continuum of the real line. It doesn't go out forever because that would be infinite. It stops at about 10 to the 308th. And in the other direction, you have 10 to the 16th numbers between 1 and a half, and then 10 to the 16th numbers between a half and a quarter, and between a quarter and an eighth, and that goes down to 10 to the minus 308. So that's how computers discretize our world. If you think about how that compares with physics, it's pretty interesting. It's incredibly fine discretization. So since I just flew here from Europe, that's a good comparison. The number of atoms in a straight line from here to London, let's say, is about 10 to the 16th. And I don't mean that's all the atoms in the Earth. I mean, in a linear sense, it's about 10 to the 16th. In fact, earlier, I think, didn't we show the number of atoms of the Earth, I said, was 10 to the 50th, which is essentially the cube of 10 to the 16th. So the Earth has 10 to the 16th numbers between Melbourne and London. That's how many numbers we've got between 1 and 2 on our computer. So it's incredibly well resolved. Physical constants are not known. I don't think there's anything in physics known to 16 digits. So they vary. Some things are known to 4 digits, or others are known to 12. Typical might be 8. So, for example, Planck's constant. I don't know if that's precisely the sharpest we've got, but it's known to 8 or 9 digits. Maybe when you guys are my age, it'll be known to 1 more digit, but it doesn't advance very quickly. It's very hard to do physics to tremendous precision. So our computers are much, much more closer to a continuum than the laws of physics. Now, this is an emotional fact for me because I didn't mention, but numerical analysis is also the most unpopular subject in all of the sciences. Everybody hates it. It's a wonderful fact that mathematicians hate it for one set of reasons, computer scientists hate it for another set of reasons, but everybody agrees it's ugly. Maybe necessary, but ugly. And if you ask them in particular what makes it ugly, they'll focus on this fact that you can't use real numbers, you've got this ugly thing called floating point arithmetic. And yet, that ugly thing is much closer to a continuum than the laws of physics. You take the gas law that Hooke and Boyle figured out with their balloons or whatever. That's only like 10 to the 8th molecules in each direction. So that's far less accurate than my field. And yet you never hear anyone complaining that, Hooke and Boyle were ugly because they wrote down this law that isn't accurate. So it's a sore point. There's another way to put it. On your computer, there is a next number after 1 because it's not a continuum. That's discreteness for you. And that's what that next number is. There's a lot of zeros in there. The other aspect of numerical analysis involving discrete versus continuous is completely different and actually much more important. So approximating real numbers by floating point numbers, you have to do it, of course, but it's not the essence of the field. The essence of the field is algorithms, and those involve discretizing things at a more interesting level. So in calculus, you take derivatives of functions. You integrate functions, for example. Well, on a computer, you have to find ways to approximate that by some discretization. And that's really the heart of the field. And I thought I'd go through an example of that to give you a sense of how complicated discrete versus continuous is. So maybe if there's one kind of overall thing I hope this lecture surprises you with, it's that the discrete continuous distinction comes up in so many different places. You can say matter is made of atoms. That's the obvious one. But that's just one of dozens of ways this comes up in the sciences. So I wanted to track through to give you a sense of the many ways. There we are predicting the weather in England. Of course it's going to be rainy tomorrow in England. It's always rainy in England. But let's suppose we're doing it scientifically. So you can start, depending how far you want to go down in your physics, let's suppose you start with quantum mechanics. Now, of course, nobody predicts weather by doing quantum mechanics. But you might say, in principle, that's what it's all about. What's the next level? Quantum mechanics is a continuum science. The next level is molecules. So how many molecules are there in a weather prediction on a scale like that? Well, maybe 10 to the 43. I make up these numbers, but they're about right. So that's, of course, a completely discrete reality. Are molecules real? Well, I think so. But on the other hand, they're epiphenomena of quantum mechanics. You know, there's a level at which they don't exist, but at another level they're real. 10 to the 43 is much too big. Nobody does weather prediction by tracking 10 to the 43 molecules. So what do? They use the great science developed in the last 2 centuries, really, of partial differential equations. The most famous set of equations of fluid mechanics is the Navier-Stokes equations, which go back to the 19th century. That's not the only equations involved here, but it's that kind of terrain. So you take this discrete reality of molecules and you approximate it by a mathematical continuum, a partial differential equation. But we have to solve the partial differential equation. So how do we do that? Well, we discretize it. And I'm making up typical numbers here. You might take that area of the Earth and discretize it by 10 to the 6th nodes in various spatial dimensions. Horizontal, vertical, longitude, latitude, and then altitude also. Fewer in altitude than the other two. But then you also discretize time. So you've taken this continuous differential equation and discretized it by not 10 to the 43, but, 10 to the 6th nodes. No connection whatsoever between the two. The fact that the molecules are discrete is completely unrelated to the fact that you're going to discretize those partial differential equations. So then what happens? You make a movie. You solve the problem, you make a movie. What is a movie these days? Well, it's got pixels in it, doesn't it? So maybe 10 to the 5 pixels. Maybe they're 10 to the 2 frames for a short little bit of weather. So that's all discrete. And then what happens? Well, we see that movie. How do we see it? It goes into our eyes, and our eyes have these cones and rods. These are discrete objects, maybe 10 to the 6th of them. That number of cones in your eye has nothing to do with the number of pixels. Well, maybe if we had a zillion times more cones, maybe we'd need more pixels in order to simulate them properly. But approximately speaking, these are just different discretizations. Then what happens? Well, the brain has to make sense of what the eye is telling it. And the brain has all these neurons. And are they discrete or continuous? Well, they're a weird mix because they're sending these continuous, these are chemical devices sending signals. But the signals are organized in discrete pulses. How are the pulses encoded? Well, the stronger the signal, the faster the pulses. So it's a complete mix of discrete and continuous. We then perceive it as a continuous flow. So, what's the truth in that picture? I don't think there's any truth. I mean, there's lots of truth. Every level is true in some sense. Is it truly discrete or truly continuous? There's no real answer to that question. So, just to give a advert, so my work for the last 15 years or so has been organized around a software system called ChebFun. So I need to ask, how many of you speak MATLAB? Wow, that's impressive. So more than half. And MATLAB, well, we mentioned it earlier, became what it is because it encoded so much knowledge of algorithms for certain types of problems. You could work with them at a higher level. You could do vectors, you could do matrices in MATLAB much more compactly and easily than in Fortran or C or whatever the languages were in the 1980s. So many of you know MATLAB. You know that what it does best is vectors and matrices, and these are discrete objects. So a vector is a set of numbers, and it might be 10 or a million numbers, but it's discrete. And a matrix is a two-dimensional set of numbers, again, discrete. So the project we've worked on is to do a continuous analog of that. And if you think, what's a continuous analog of a vector of numbers? Well, it's a function, maybe a smooth function. So in ChebFun, we try to overload the ideas of MATLAB into continuous analogs. So it's interesting. You're a young audience, so let me ask, how many of you know the idea of overloading something in a computer language? Yeah, so that's great. And these are all the young people, of course, in the room. But this is one of the ideas at the heart of object-oriented programming, which became big 20 years ago, is to overload concepts and give them new meanings. So you take a vector, you take some syntax in MATLAB that means a discrete vector, you overload the very same syntax to have a new meaning as a continuous function. And what happened with ChebFun is that idea had become big. Overloading of things was in the air. Object-oriented programming was in the air. And we were also very good at the mathematics of Chebyshev approximations of functions. So the idea was to use that mathematics and devise an overloaded system of MATLAB. So all of you who raised your hand for MATLAB, I now ask you, please, after this lecture, Google ChebFun. Download it. It's free. If you've got MATLAB, you've got ChebFun, and play around. And we've got a great website. It'll show you some neat things. I don't know why anyone does MATLAB anymore when there's ChebFun. Okay, so I think that finishes numerical analysis. And now, more broadly, if you like, let's talk about computer science. So raise your hand if you think of yourself as at heart a computer science type of a person. Yeah? Okay. By the way, my career has oscillated between the two. I was an undergraduate with Bill Gates in mathematics at Harvard because there was no computer science, except, of course, he was doing computer science. Then I went to graduate school in computer science, and then I did a postdoc in math and computer science. Then my first job was in math, my second was in computer science. I went to Oxford in the computer science department, and then our group moved into the mathematics department. So I'm totally a mix of the two. There's some fascinating scientific sociology here. So computers basically arrived in the 1950s, and computer science quickly thereafter was created as an academic field in the 60s. And in 1963, there were like one computer science department on Earth. By 1968, there were probably 50 computer science departments. It's an amazing thing there. Now, people like me, the numerical people, were among the leaders in creating these departments. And the reason is, in the 60s, numerical computation was obviously the main thing computers were for. Obviously, computers could do other things. They could store financial records. You had languages like COBOL, for example. Everybody knew that in principle you could have artificial intelligence, even though it couldn't do much in those days. But the great bulk of computing was numerical. Solving differential equations, all that stuff. But that changed. A bifurcation took place. The field grew enormously, and when fields grow, they subdivide, don't they? That's why we have pure and applied mathematics, because of growth and subdivision. Well, similarly, it happened in computer science. And roughly speaking, the people who call themselves computer scientists for the last 50 years are the discrete types. They like discrete problems and discrete algorithms. And the rest of us who had founded their departments for them became less and less welcome in those departments that we had founded and have drifted into mathematics departments. It's quite remarkable. And I say it so simply there, but that's a pretty good description. That at least until the last 10 years, I would say, numerical analysis was the study of algorithms for continuous problems. Computer science was the study of algorithms for discrete problems. And these are two legendary figures in these fields who epitomize on the left numerical analysis and on the right computer science. Both well, Knuth is alive and Golub is dead, but both at Stanford, and they know each other very well and actually good friends, which is more than you could say for all numerical analysts and computer scientists. And both were very important in my life, by the way. I want to say a little more about this because I'm an academic and I'm so fascinated by these sociological things. So the theme here is that we've had a bifurcation in computer science where the discrete people have gone one way and the continuous people the other way. So here is a table of contents from the olden days. So 1958, I think this was the oldest one I could find. It's volume 5 of the Journal of the Association for Computing Machinery, an old-fashioned name. Now, there you see a bunch of titles of papers. And if you look at those titles, you can tell immediately, if you're in the field as I am, which are essentially numerical and which are computer science of the other kind. And roughly those are the numerical ones. So if you see orthogonal polynomials, Chebyshev, there he is. Dirichlet problems in a domain with corners, the Runge-Kutta single-step integration, characteristic equations, that's eigenvalues, curve plotting, conference on matrix computations. Those are all numerical analysis topics rooted in continuous mathematics. And then the others are the minority. Those are automatic preparation of flowchart listing. I mean, that gives you a sense of how primitive the other side of computer science was in the early days. I mean, flowchart listings, that's, you know. Simplification of a class of Boolean functions, so that's a more mathematical topic, but on the discrete side, and so on. So that's the way it was in the early days, before the bifurcation. So now I take the most recent one I could find. Notice how everything has changed. The visual impression is completely different. It's more modern. They have changed their name from the Association of Computing Machinery to the ACM, which that doesn't stand for anything anymore. So I will now highlight all the articles with a numerical flavor. Okay, I've just done it. There aren't any. No numerical person would ever publish in this journal, almost. It's just vanished because of the bifurcation. Both fields are healthy, but they're no longer the same. Here's an unrelated but amazing fact. In the earlier one I showed you, the average length of the paper was 10 pages. Now it's 40 pages. What do we make of that? It's an amazing change. So for those of you who, you know, are the age I was when I started, does it imply that it'll be 160 pages? You know, when you're my age, you'll have to write a paper 160 pages long? I don't know. My other computer science topic is computability and complexity. So computer science has at its heart a beautiful subject of complexity theory. It goes back to Alan Turing. It's amazing. It's exciting, beautiful theorems that have real implications. And the whole style of that analysis is discrete, essentially. It sprang from logic. Turing was outstanding at logic and things related to that. The idea of a Turing tape, if you know that idea, is a tape is a continuous thing, but it's divided into discrete squares, so that's a discrete idea. And P equals NP is this famous million-dollar question. That's a discrete question. It's either true or false, and it's all about discrete algorithms, which it is. People have tried to make a similar theory for continuous algorithms, and they've made one, and Smale is one of the most famous mathematicians on Earth. These are not, you know, children. But it's had very little impact, strangely, and I don't fully understand why, but there's no doubt that the heart of complexity theory in computer science is discrete. I mentioned a moment ago the last 10 years. Things are really changing. So now we hear about machine learning, for example. And in the summer school, they were telling me how big the different courses were, and I forget the names, but the one that's close to big data and machine learning is like 104 times bigger than all of the others, right? Because that's what everybody wants to study these days. Something surprising has been happening. Recently, even for the discrete problems, people are using continuous algorithms. And the way we interact with our computers, it sort of has a discrete flavor, but underlying that, it's funny how the algorithms are more and more continuous. Machine learning is, at its heart, a kind of a continuous optimization subject. The computation has this continuous flavor, but the final result is discrete. It's yes or no, or that letter is an A, or that car is a Toyota, or that image is, George. The outputs are discrete, but the algorithms are getting more continuous. And here's a book in that area. For example, this famous field of P equals NP, NP completeness, has at its heart a collection of 1,000 important problems that are all in some sense equivalent. But it turns out they're not entirely equivalent, and one of them, for example, it's just an example, is called the max cut problem, and it's an NP hard problem. But if you're willing to solve it not quite optimally, if you're willing to be 13% shy of optimal, it becomes an easy problem. Isn't that weird? It can be solved by semi-definite programming, which is a standard eigenvalue-related method, and it's continuous. So you have this effect that discrete problems can be unbelievably hard if you truly need to solve them down to the last ounce. But if you're willing to approximate them by continuous problems, you can do sometimes, not always, very well. This book is about that kind of thing. And this theme is becoming more and more important in computing. So in fact, I think finally, as we look forward to the next generation, the discrete and continuous sides of computer science are probably coming back again. And if you're in that area and you want to be really influential, you need to pay attention to both sides. Well, this is a question I wonder about. P equals NP is all about whether certain things take exponentially long to compute. That almost begins to look like maybe somewhat of an artifact of having posed the question in an excessively narrow way. But that's sort of another subject. Okay, I think we're down to our last two topics in the area of technology. So first of all, let's talk about hardware, digital devices. So, I'm from the analog generation. The phone I used as a kid was analog. The phones we use now are digital, of course. And my kids are from the next generation. There's a random picture. So a picture like that is interesting because nowadays we're completely familiar with that kind of thing. But if you're as old as I am, you remember the first one you ever saw, at least for Americans. It was a picture of Abraham Lincoln. Is there anyone in the room who knows the picture I mean? Yeah. And that was mind-blowing, and it was coarser than that. It was maybe, 15 by 25 and black and white. But you could make out the stovepipe hat and all. It was amazing. And it's really thrilling to see this extreme case of discretization. But now we're so drowning in this, it's completely familiar. You probably can't tell what that image is, but if I refine it a bit, you can sort of see, and it's actually, it's an image from Oxford of punts under Magdalen Bridge. This is completely routine to us all now. We all know that all the images we deal with look like continua, but are made of discrete objects, pixels. There's this wonderful quote by one of the heroes of the early years that reality is 80 million polygons per second. I think he died before that could be achieved, but when Toy Story came along, by the time we reached that era, people were able to do very convincing things, and now, of course, it's unbelievable. So I really don't approve of video games, at least of the kind that young men tend to play, but probably some of you know these games. I don't even know them, but I'm told the level of realism is sometimes astonishing, right? I don't want you to raise your hands now. This is too upsetting. Steve Jobs did many things. He founded Apple and then did it again, more or less. But among the things he did, he's the one, as much as anyone, who made the world take the transition from analog music to discrete music. He called up his friends like Madonna and persuaded them to make their tunes accessible in the digital universe. So when I was a kid, music was sold in albums. Thanks to that, it became, well, it was no longer sold maybe, but in any case, it became song by song. digitized, complete change. Most of you are too young to imagine any other way. Well, as I've already mentioned this, I guess, despite all that, the kind of device, well, nobody has one of those devices anymore, but the sort of devices that we use all the time, although digital devices are more and more using continuous algorithms. Okay, and I think my last topic was nanotechnology, another one that Feynman is connected to. So there's a picture, pretty old one by now, of one of the dramatic early things that was done by the physicists at the interface of continuous and discrete. So what you see there is actually, it's a false color, but a false color representation of a genuine measurement of a collection of atoms in a ring. So they really were able to measure these atoms and in some sense to measure a quantum state inside the corral. Once that sort of thing starts happening, you begin to have technology that can work with the molecules and the atoms. So back when Einstein was doing his things, people didn't even completely believe in molecules. They had to be persuaded. And they certainly couldn't work with molecules individually, let alone atoms. But in the last 20, 30 years, it's begun to be possible. So people can now manufacture things atom by atom. That's not how most manufacturing is done, but more and more can be done that way. Feynman had this wonderful quote, there's plenty of room at the bottom. He wrote an important early paper in this area. The word nanotechnology was created a bit later. The scanning tunneling microscope is a microscope that really detects the individual atoms. Fullerenes were one of the early chemical discoveries that were at the interface, sort of designer chemistry. 3D printing is different, by the way, because 3D printing isn't about individual atoms. It's still treating, the substance you're working with is a continuum, usually. But on the other hand, you're driving it with discrete pixelization. So 3D printing is a discretization in order to manufacture things. And again, you take this for granted. In the building, you know, the mathematics building that I spent today at the other campus, you have these unbelievable demonstrations. In the case, you know, there's a case of these 3D printed objects. It's all discretization applied to giving us greater power. Okay, so I want to summarize, wrap up, first of all with a few dates. So I'm, again, 14 topics, and I'm telling you, I'm rounding to 50 years, and I'm telling you when things happen. Atoms sort of were invented twice, at Dalton and then Einstein. I'm giving them both credit. Chemistry, we had Mendeleev, Dalton, I guess. Biology, cells are old. DNA is much newer. In mathematics, the oldest of all of them was the uncountable stuff. Well, the irrational stuff, sorry. Algebra analysis, well, that's sort of always been with us, but maybe in the 19th century was when that bifurcation became important. Numerical analysis is very much from the computer era. Computer science also from the computer era. Technology, a little bit more recently, are these big discretizations, the discrete side. So if you look at that history, what you find is the last few hundred years have changed the way we view the world in all sorts of ways. Loosely speaking, 500 years ago, everything looked continuous. And now we have a blend where a lot of things we realize at some level are discrete, even if at other levels they're continuous. Here's a footnote. So there's one person who individually made huge contributions to 5 of the 14 topics. Anyone want to guess who that is? Well, that's not the one I'm thinking of. It could be, because he was amazing. Yeah. He was unbelievable. The other one that I'm thinking of, any other guesses? Who? That's the one I'm thinking of, yeah. And so I know he did. Whether von Neumann did, I'm not sure. But there was Turing, who did not live to be very old. Neither did von Neumann. And these are the 5 in biology. He's the first guy who tried to make a theory of how biological things became discrete. He was pretty much the first guy to study rounding errors in floating point arithmetic, or fixed point arithmetic. In numerical analysis, he was the first guy to use sort of computer-style algorithms to try to solve the Riemann hypothesis. He failed, but actually if the Riemann hypothesis were, if there were a counterexample, the chances are Turing would have found it in 1943. In computer science, of course, that's what he's most famous for. He's less famous for the stuff he did of a truly technological nature, but in the war and then after, he created one of the first computers and one of the first adders, all about how to interface discrete and continuous. So, let me summarize. So, to the proverbial caveman or woman, I think it's safe to say that the world was continuous. Over the years, in complicated ways, in one subject after another, we've discovered there's a discrete side to many, many things. And it's certainly true that the power we now have with science and technology depends on mastering those ideas and that technology. But it's all subtle. And this, to me, is the wonderful subtlety about it, that often the implementation, you could say, is really discrete. And yet, it doesn't follow that you could get away with discarding the continuous versions. That's somehow also really there. You know, concepts. Are concepts really there? Well, I don't know. But you can't get along without them. At least that much is true. So, I mentioned this earlier, that there is a trend that often junior people find the discrete side more appealing. In fact, I was surprised when you raised your hands that there weren't more of an imbalance towards the algebra side. But as you get older, sometimes that looks like the harder. With deeper understanding, sometimes the continuous proves simpler. There's an educational side of all of this stuff, and most of you, young, so pay attention. The old guys in the room, or gals, are pretty much steeped in one side or another. We can't change. It's too late for us. But if you really want to be important in the future, you need to pay attention to both. And I'm especially thinking of people who are sort of broadly speaking, in the computational, mathematical, getting things done side of our world, which is half of our world these days. You've got to pay attention to both the discrete and the continuous. So I wanted to finish by coming back to this image that we began with, which to me encapsulates so many things. So let's mention a few things we see in that image. First of all, of course, it's really made of dots. There's no doubt that it's a lot of dots. But then again, it's also true that it's really got some lines in it. You know, those are not random. The lines are really there, whatever that means. You couldn't possibly describe that image without noting that it has lines in them. Then you have the weird feature that at the left, the lines are vertical, and at the right, the lines are horizontal. You know, so where is reality in that? You know, could you say that they're truly vertical or truly horizontal? Well, of course not. And in the middle, they're neither. They're not lines anymore, they're just a grid. I think that's an analogy for almost all of the things I've said this hour, that the discreteness is somehow there in the underlying reality. But that doesn't mean that you can ignore the continuous, because that's also there in the conceptual reality. That might be the end. Yeah, that's the end. Thank you.
Thank you very much, Nick. We've got time for questions. Anna? Do we have any questions at the moment? One of the things that has been in the news with the Australian recently is the progress of quantum computing.
Oh, yes.
Do you think there is what do you think about the change in the computing structure
Isn't that
in the near
interesting?
future?
Yeah.
Do you think there will be a move from discrete to continuous in that?
You've all heard of this, I guess. What was her name?
Michelle?
And is she in Melbourne or somewhere else?
Sydney.
Right.
UNSW.
Yeah. Oh, you're asking the wrong person. So when quantum computing, 20 years ago, they started saying this would change the world, and I was skeptical then. Now it's, compared to normal computers, it's still this big. But they still say it'll change the world, and these people are not fools, so I suppose it will. I don't think I'll live to see it. I think it's going to take a long time. Aren't they now trying to, she got this award for moving towards a machine with 20 bits, right?
I think so.
Yeah, so the traditional computers have more than 20 bits.
Yes.
Yeah.
Yes.
Oh, good idea. Oh, was it? Ah, right.
Yes.
Yeah. Please, come on.
I guess one way that you potentially could describe the endeavour of science is the search for truth, in some sense. Do you think that some of your observations kind of talk to the fact that truth really depends on the level of description that you're applying, the extent to which any description leads to being able to understand something or being able to know what's going to happen.
Yeah.
How do you think we impart that idea to people rather than sort of getting fixated on the idea that there should be a clear-cut distinction between things that are true and things that are false?
Well, that's an amazing question because you started with philosophy and you ended up with education. You just covered everything. I don't know what to say. To start with the philosophy, I'm a materialist. I don't myself believe in God, and I don't even believe in consciousness. I think all of you are not conscious, and I too am not conscious. Admittedly, I feel unconscious, but I don't actually believe it. So I believe in some sense reality is just a lot of stuff meaninglessly bouncing around. If you want to think of molecules just bouncing around, we don't really exist at some level. And yet, of course, at another level, that's ludicrous. Obviously we exist. It's very hard to square this materialistic view of things with the other reality. As to the educational side, I don't think I have any special ideas there. It's very important. People have to understand that different concepts are important at different levels, which is what you're emphasizing, right? If you want to do design of computer hardware, you're at one level. If you want to design the operating system, it's another level, and genuinely different concepts are important. Let's be very specific. Back to numerical analysis to be on safe terrain. People tend to think that to do that subject, you have to know a lot about floating point numbers. I don't agree. I think for most of that subject, you can pretend that computers use real numbers. It's the wrong concept. To focus on that underlying reality is irrelevant to the algorithm. So I agree with you, different levels.
Okay. Hi. I was just wondering, this is a generic question, of course, what sort of advice would you have to somebody who's at the level of finishing high school, for example, and choosing what to do with their life, whether to go on to university or not, and if so, how to choose a subject and all that sort of thing? Is there like one nutshell of advice that you would have, or is it just too big a question?
Is Andrew Elder in the room? No, you're not here? Okay, he was maybe going to come. He's not laying low, is he? Because now I might reveal something I shouldn't. So I first visited Melbourne when I was 16 and his mother was 14. And I spent last night with them, so I've been visiting this family. And it's absolutely fascinating to think of what you were focused on back then and to translate it forward 45 years. And it was very striking to me that I went a very academic route, which was right for me, and she, this old friend, went a very different route, which was spectacularly right for her. And I'm very impressed with how people differ, and we each have to find what feels right. So I guess all I have to say is that don't do something that doesn't feel right. My wife spent 8 years as a lawyer. Even on the first day, she knew it was wrong for her. Don't waste 8 years of your life. Well, I could finish by saying being a lawyer, but doing something that doesn't feel right.
So you mentioned before with machine learning, things like that. I imagine it being where... here we go. Jeez. All right, so you mentioned before with machine learning something along the lines of they process discrete events and things like that, but sort of continuously learn and all that. Now, I can imagine it working quite well on the discrete side of things, but in discrete problems and things. Yeah. But you also mentioned the continuous side of things aren't really as widely publicised in the computer science world. How do you find that machine learning sort of works on continuous problems?
That's a good question. And do you have one in mind? What would be a good example?
This is exactly where I have no idea.
Yeah. Of course it must, but I'm having, offhand I'm not thinking of one, because, we interact on our phones and it's usually something discrete. We want an answer which is a discrete thing. Oh, but there must be somebody give me an example,
What about some of the striving systems?
Yeah, they have a continuous flavor. So the question of what route to take is essentially a discrete one, but the question of how much to accelerate at any moment is a continuous one. So maybe that's a good... I'm not an expert at all in machine learning, but I can certainly see how important it is. And one thing, if you go through a scientific career, you see fads come and go, and some of them you later realize weren't that important. And for mathematicians, I hope I don't offend anybody, but a very big one at one point was called catastrophe theory. And most people now think that wasn't as important as it was made out to be. On the other hand, other fads, chaos was another one, and in some sense that really is as important as it was made out to be. I believe machine learning is one of the important ones. It's totally changing everything in almost a terrifying way.
What do you think of mathematicians who don't believe in real numbers? Their opposition is basically in the sense that they're not computable.
Yes.
Okay, and so also corollary to that is they don't believe in infinite sets.
Yes, so I'm totally not an expert in that point of view. Do you actually study that subject? Yeah.
I met some mathematician in the internet who I would call, they will be ultra constructivist, you might say.
Yeah.
That's the kind of philosophical point of view, and maybe that's also a thing about philosophical mathematics that comes into play within discrete and continuous.
So a question like that has many different aspects, because there's the philosophical side. Does the real line exist? I don't have anything to say about that. But also there's the more research mathematics question of what sort of proofs are legitimate. And I guess I'm pretty traditional on that subject. I'm with Hilbert. You can do pretty much anything. Without answering your question any further, let me mention to you all one amazing aspect of these different infinities, which is that the rational numbers that's the smallest infinity. Integers, rational numbers, they're all the same. But ever since Turing, we've known that actually all the numbers we can ever talk about are also at that same smallest infinity level. So although the real line, insofar as it exists, is a bigger infinity, all the numbers we can identify by any means whatsoever rigorously are a countable set. They're all in the small infinity. So in that very precise sense, almost all of the individual numbers in the real line can never be talked about. Does that mean they don't exist? Yeah, well, I don't know what to say about that.
You mentioned that exponential time algorithms might just... exponential time algorithms might just be an artifact of the discrete setting in which they operate. I find that a really intriguing idea, and it sounded like you had a bit more to say about it. Do you?
Okay, you said it very strongly, might be jest. There's no doubt that there will be contexts where the whole P equals NP question is absolutely on target. But I'm guessing that will in the end be the minority of applications. Actually, I just wrote an essay on this. If you Google, if you can spell my name, look up, oh, I'm digressing. Is there anyone here sufficiently clued into American baseball to have heard of Yogi Berra? Good, okay. So Yogi Berra said a lot of interesting things, and I've written an essay on this subject you just mentioned called Inverse Berraism, so look that up. But anyway, to the question, when I was in graduate school, the P equals NP stuff was already there, and this is complexity theory in computer science, and the idea is that some algorithms have worse complexity than others. And the faster your computers get, the bigger the divide becomes. So back in the 1980s, if it was hard to solve a traveling salesman problem compared to inverting a matrix, you fast forward to 2018, that gap should have widened unbelievably. So the prediction in 1982, when I got my PhD, would have been that by 2018, the gulf between the polynomial problems and the NP problems should have been light years across. That's not how it's worked out. So if you actually look at how people compute, you find that many of these seemingly almost impossible problems are being solved all the time. So the traveling salesman problem is an example that people are much better at that than anyone ever predicted. Another even more remarkable example is in logic, they have these algorithms for so-called satisfiability, where you compute whether certain logical expressions can be made true or false. That's an NP-complete problem, so it's in some sense believed by everybody to be in principle almost impossible. But the set of examples where it's so hard is negligible. So in practice, not only is it possible, but it's become a technology that people rely on to solve other problems. So I believe in all sorts of ways that by the time somebody wins $1 million, I think the problem of P equals NP will actually be less important than we thought it was 30 years ago.
Sorry to poach that from you there. I just had a quick question. Just because we're very used to looking at the sciences and the mathematics, what did you actually think about the question of discrete and continuous into turning it into more of a human sciences perspective? Do you think there's an application there, or do you think it's mainly best to keep it within the mathematics and science?
I have to ask you, do you have one in mind?
The only real thing I could think of was sort of economics or psychology. In terms of economics, where you actually have this machine learning that actually, like the automated sort of systems of buying and selling stocks to an extent where selling and buying things are happening at such a fast pace that you could almost consider it continuous.
Yeah.
But yeah, I couldn't think of any other examples.
That's fascinating. I certainly don't have an immediate thought on that subject. My wife is in English literature, and I think for her this distinction has no significance. But she doesn't represent all of the humanities. How interesting, yeah. I have to mention one thing, though. So I hang out in New York for 6 weeks a year. And as I was walking along as a pedestrian on the sidewalk, you tend to think of yourself as part of a continuum. You're a particle in a flow, right? And of course, traffic of cars and pedestrians is modeled that way. But then, when you come to the corner in New York, you're not allowed to cross as a pedestrian until there are, sorry, I said that wrong. A car is not allowed to turn across until there are 0 pedestrians in the crossing. So it's not a continuum, because if it were a continuum model, you'd never get to 0. You'd merely have a very low density. But there are things where something you might think was well modeled continuumly in our social world has to be discrete.
So I guess I had a question with regard to, I guess, like most mathematics degrees don't particularly involve much explicit education on like logic and symbolic logic, and in fact symbolic logic seems to be almost banished to the arts and philosophies, yes, schools on the other side of the campus, literally. But I mean, I did some in my degree, and I found that it was actually probably like it gave a lot of light to what I was implicitly doing in the mathematics. And so I guess I just wanted to ask, like, did you ever have like sort of subjects that you sort of covered just out of interest that then gave light to your research and your work? Like, and do you think that some of this like floundering around the topic can actually really help give light to?
Oh, I passionately believe in that, and when you're young is the time, because as you get older, it's very hard to learn new subjects. For me, of course, a lot of this talk was about the physical sciences. I was a math major in school, but I always took physics courses sort of just because I did, and that's been hugely important. Yes, I think, absolutely. Try to get a lot of stuff in before you're 30, because after you're 30, you won't do it so much. I thought you were going to ask me what I thought of logic, and thankfully you didn't.
So hi, like thanks for the talk.
Who am I listening to?
Yeah.
Oh.
Yeah, thanks for the talk. This is more of a personal question. So what, I guess, got you into mathematics, and what keeps you interested in mathematics? And in the future, like, what do you think will keep you interested in mathematics?
Oh, I'm hooked for life. There's no doubt about that. I'm sure many of you are familiar with the idea that mathematicians are the people who never do anything else, because it's in school right from the beginning, and if you're good at it, and of course I was good at it, you just keep doing it and you sort of never leave. And I was like that. But by contrast, for example, engineering is not usually in school. So in order to become an engineer, you have to sort of take that step. And mathematicians are the ones who never take that step. But I have to say, it's really wonderful how if you keep doing science or mathematics or whatever, what you know grows with the years. And when I was in university, I guess I more or less figured that you learn things until you're 21 or 2, and then you're an adult, and that's sort of it. And now that may be true for people who go into, some sorts of jobs, but if you stay paying attention to science or mathematics, it's just amazing how you keep learning more and more things, and it's thrilling. I feel that now I have much more perspective about how things work than I did 10 years ago. So for me, it's just exciting how it grows and it grows.
I wanted to ask you a question. You said earlier...
Where are we here?
Here.
Oh, yeah.
You said, somebody said that you were the first commercial customer of MATLAB.
Yeah.
And then later on you mentioned that nobody uses MATLAB anymore. I
didn't mean to say that.
No.
No, can somebody help me? What remark are we thinking of? What did
I was going to ask you, what do you use?
Oh, I'm sorry. We're in connection with JEDFUN. Oh, I wish they would stop using MATLAB. That's what I meant to say, because it's so 20th century, that whole vector matrix way of thinking. But regrettably, they're still doing it.
Yeah.
Was that, did you have more you wanted to?
That pattern up there, how was that generated?
I did that a few years ago, and I don't remember. Well, I wrote a MATLAB code, of course. And actually, the quality is terrible. Those ought to be little dots, and they have some shape that they shouldn't have. Yeah.
Okay, cool.
No, over here. So at the start, you gave a fascinating quote from Feynman about, if you had to destroy all of science except for one sentence, what would you keep? All right, so same question to you, but limited, like you had to destroy all of mathematics except for one idea, and no cheating by rephrasing Feynman's statement either.
Well, I'm a continuous guy, so I guess for me, derivatives and integrals are, how can you find anything to compete with those? But that's a terrifying question.
So what's your view on pure algebraic mathematicians and mathematics?
I didn't hear the pure what?
Pure algebraic mathematicians.
Pure algebraic mathematicians?
I mean, the other side of math that you are working on, and mathematics, yeah.
So my views are complicated. I'd have to say I respect me more than they respect me. So, so in my less charitable moments, sorry, we need to digress again. Do you know the joke what's the difference between an etymologist and an entomologist? And the difference is an etymologist knows the difference. So now let's ask, what's the difference between a pure mathematician and an applied mathematician? And the answer is, an applied mathematician thinks there's a difference. Because what you often find is that pure mathematicians, who are often very brilliant, there's no denying that, tend to assume that, you know, who needs applied mathematics? We've got it all, you know. We use our genuinely impressive skills to analyze the world. Applied people like me talk to those, and we discover they don't really know anything about the world sometimes. So on the one hand, I have this, you know, skepticism about, as it were, the scientific standing of a lot of pure mathematics. On the other hand, there's absolutely no denying that the stuff that lasts the longest tends to be the fundamental pure mathematical things. And nothing I do will be remembered in 100 years, but we have Andrew Wiles in my building, and what he did will totally be remembered in 100 years. So it's pretty important.
I think we'll just stop there.
Oh, okay. Was that answer particularly bad?
No, it wasn't particularly bad at all. But, I can see it's going till 9 o'clock. Yeah, I'd like to thank Nick on behalf of the summer school for a wonderful talk and being prepared to share all of this with everyone here. So thank you very much.